Hey guys, here's your notes on pitch and volume. After you investigated it, first thing we're going to do is pitch. So the pitch is basically the note you hear. I'm going to do a couple weird things with my voice here. So here's a high note or high pitch, and here's a low note or low pitch. Notice they're about the same volume when I said those two different pitches, but one was a different note. And what's different about those two sound waves I just made is the high pitch one actually has a higher frequency, so there's more waves packed every second. My vocal cords are vibrating quicker to make this sound, and they actually are like waving really slowly to make this sound. Okay, so the frequency determines the pitch or note that's made. So as you know, high frequency waves, they're all packed together because they're made quite often, and low frequency waves are spread apart because they're made less often. So that's what a sound wave looks like at a high pitch and a low pitch. But in the title, they're different pitches, right? But they're the same volume. How do we know they're the same volume? The same volume because they have the same amplitude. Oh, I just underlined it right down there. So the same volume. Those two sound waves because they have the same amplitude. It's just one's more packed together, high frequency, high pitch. When we talk about pitch, we talk about musical scales, and I really like music, so I'm going to teach you guys a couple things here. So here's an example of a chromatic scale. It's just one musical scale, and musical scales from maybe it's the Sound of Music, do, a deer, a female deer. Kind of that song, that's where I learned it from first, right? And a musical scale goes do, re, mi, fa, sol, la, ti, do. Alright? And it goes back to where it started, basically. Or if you sing it nicely, it's like do, re, mi, fa, sol, la, ti, do. And each of those sounds correspond to a frequency because the note or the pitch is changing. So we start at a low frequency, do, re, mi, fa, sol, la, ti, do. And as you get to the do again, you're at a much higher frequency or higher pitch. Now, and each one of those frequencies is a note. So starting at C, we go up from there, D, E, F, G. And there's no H note. If you don't know music, there's no H. So you go back to A, B, and then when you get to do again, you're at the note you started with, which was a C. And the C and the C, from here, jumping all the way to a C again, those are separated by an octave. All right, so that's one octave up. The 524 hertz sound is an octave higher than the 262. Well, isn't there some relationship between those two numbers? You might not see it right away because they're not kind of round numbers. But if you take the 262 hertz, which is a C, and the 524 hertz, and basically what's happening at the 524 is you start the whole process over. There's a new scale that starts there. A new octave scale, right? So if you go from the 262 to the 524, which is C again, what you've done, I'd like you to actually do this. Multiply 262 on your calculators by 2. So just multiply that by 2 and see what you get. And I'm just going to stop here until you do that. I'm trusting you. I hope you did it. Alright, before I reveal that 262 times 2 is actually equal to 524. So when you go up an octave, what you've done to your frequency is you've doubled it. Whenever you restart that scale, you've doubled your frequency. Alright? And it's kind of a cool thing, So what would be the next octave, the next C note? What frequency would that be? Well, what you would do is you take 524 and you'd multiply that by 2 to get your next C note. So 1048 would be 524 times 2. And if you want to get the next C, it would be, well, I'm trying to do it in my head, 296 hertz would also be a C, and it would be where another octave starts. All right. So there's your musical theory lesson. All right. Besides pitch, we really want to separate pitch from volume. They're two separate things, and musical scales have to do with pitch. Volume is different. The volume of sound produced depends upon the amount of energy in a sound wave, and it's expressed through amplitude. All right, so the amplitude of a wave, that is, right here, the height of it, tells you the volume. So here's a high volume, high amplitude wave. Lots of energy, really loud. If the volume gets high enough, it could damage your eardrums. Definitely. So a low volume, the only difference is that's a low amplitude. Not a lot of energy, can't damage your eardrums. All right. Notice that this is a high volume wave, but it's not necessarily a higher pitch wave. These are actually the same note being played. And you could tell because the wavelengths are just as long as one another. If one had wavelengths squished, it would be a higher pitch or higher frequency, but it's not. They're spread the same, so they play the same pitch. It's just that that one is louder than that one because it's taller. All right. So same frequency and they're the same pitch. All right. A higher pitch wave would be more like that, right? But that's not what we want to show here. We want to show the same pitch, so same spread. All right. Last thing about volume, there's a unit for how loud something is. Decibels, dB. All right. So that's your unit for volume, right? Yeah, so what was your unit for pitch? Well, obviously, pitch is frequency, so hertz was your unit for pitch, you know? Decibels, and a good example of decibels is the, we could say the alarm, fire alarm. 120 decibels. Very close to the threshold of pain. And that's why volume or amplitude tells you the amount of energy, because that energy eventually could burst your eardrums at 120 decibels if you get too close to it.